In this video, we're going to look at some examples of redox single replacement reactions, and we're going to try and predict the outcomes of these reactions by calculating the voltage. So I've got magnesium metal being put into a solution of silver nitrate. Now the first thing we need to do is figure out what's going to be replacing what. And since I've got magnesium metal, and silver is obviously a metal, hopefully all of you know that, this magnesium is going to try to replace the silver. So this is the reaction that's going to be trying to happen, is magnesium replacing silver. So this magnesium, we've got magnesium here, plus, and then the silver. This is the real business that we want to keep track of. This is our generalized reaction. And we're wondering, will these trade? And if this trades, then magnesium is going to take on a +2 charge. So really we would need 2 silvers here. And then the silver is going to take on 0 charge. We really have 2 silvers there on the outside. So what are the half reactions that we would have here? Well, I would have magnesium. I would be trying to get rid of 2 electrons in order to become ionized. And then we're going to have this silver ion, which needs to pick up an electron in order to become the silver metal. Okay, so which one of these is a reduction reaction? Well, silver would go from a plus to a 0. So this would be my reduction reaction. So my reduction reaction, that's going to be the voltage that I read on my reduction potential sheet. My oxidation reaction, which this is my ox, that is the one that I'm going to need to flip the voltage for. Okay, so let's go check out a sheet. Let's go check out our data table. If I find silver here, silver right there, hey, look at that. It's going to be plus 0.8. So this silver reduced is going to be plus 0.80 volts. And now I just need to find the magnesium. Magnesium is, oh, it's right there. Negative 2.36 volts in the reduction side. So when it's oxidized, it's going to be a positive 2.36. So here, this one's going to be positive 2.36 volts. And so when I add these together, I'm going to get 3.16 volts, positive 3.16 volts. And since this is positive, since it's a positive voltage, this reaction will proceed. And so I'm going to get silver all by itself as a solid, and I'm going to get magnesium nitrate. It's going to be 2. It's going to be aqueous. So I need to make sure I'm keeping track of my my positives and negatives there in my ions. And then all I need to do is balance this. And so I'm going to put a 2 here. I'm going to put a 2 here. Perfect. And that's my completed reaction. Let's do another one. All right, let's look at cobalt and iron 3 chloride. Is this going to react? Well, first off, what's going to be trying to replace what? Well, the cobalt, that's a metal. Iron, that's a metal. So the cobalt is going to be trying to replace the iron. So we can go ahead and draw out our generalized reaction here. Cobalt plus, and then it's going to be FeCl3. So that means this is Fe3 plus. And so we're wondering, is this going to turn into Fe plus CO2 plus? Now, sometimes we're going to have elements that can have more than one ionization. Whenever we have that, I want you to go ahead and pick the 2 plus option. That's going to be one of the more common ones. It's going to be the right answer more often than not. If we just can't predict it, we'll go with that one. So next, let's write out our half reactions. First, we've got cobalt potentially becoming cobalt 2 plus. It's going to be cobalt. And in order to become cobalt 2 plus, it needs to give away 2 electrons. It needs to get rid of some of that charge. Okay? And so this is going to be my oxidation reaction. All right? So we know that this is going to be the reaction where I'm going to have to flip that voltage. All right, and then I've got my iron, Fe3 plus, and that's going to try and pick up 3 electrons in order to become pure iron. So now let's look at our reduction potentials. Well, let's label this first. This is a reduction reaction. So then let's look that up. Let's start with iron. Let's find iron on here. If I look for iron, I should be able to find it. It should be, hey, there it is. Iron right near the top. And so as a reduction reaction, it's going to be negative 0.04 volts. So this iron is going to be negative 0.04 volts. All right, and then what about my cobalt? Remember, this is going to be oxidized, so it's going to be the reverse of whatever we find. Cobalt here, there it is, cobalt 2 plus, negative 0.28 volts. This is going to be negative 0.28 volts, but because it's the oxidation, that sign flips. So the reduction of cobalt would be negative 0.28. The oxidation of cobalt must be positive 0.28. So then all we have to do is add these together, and we can see that 0.28 plus a negative 0.04, well, that's going to be a total of positive 0.24 volts. And so we see that it's a positive, so this reaction will proceed. So we'll have cobalt as a 2 plus bonding with that chlorine, taking over that chlorine from that iron, and that iron being freed up. And so then we just need to balance this. So I've got 2 chlorines and 3 chlorines. Okay, I'm going to balance that first. I'm going to put a 3 here and a 2 here. And now my chlorines are balanced. And then I just put a 3 by my cobalt and a 2 by my iron. And there we go, all balanced. Let's look at one more. All right, here I've got chromium trying to bond and replace the aluminum in aluminum chlorate. So first I've got my chromium. I've got chromium as a regular thing. And then aluminum, well, aluminum's always going to have a +3 charge. And what's trying to happen here is this aluminum would try to become solid aluminum, and the chromium try to become Cr2+. So let's write out our half reactions here. The chromium is going to become 2+, so it's going to be Cr. And in order to become the Cr2+, it's got to lose those 2 electrons. Then the aluminum is 3+. And in order to become regular aluminum, it needs to get 3 electrons. Okay? So which one is reduced? Which one is oxidized? Well, aluminum here, that's going to be reduced. Charge getting reduced. And the chromium here, that is going to be oxidized. Great. So whatever value we find for aluminum, we can just use that one. Whatever value we find for chromium, we're going to have to flip it. So aluminum, if we look on here, oh, hey, right there, negative 1.66. It's going to be a negative 1.66 volts. Then the chromium, let's find that. Chromium 2+. Hey, right there. Negative 0.91, and since it's flipped, that means a positive 0.91 volts. Then when we add those together, what do we get? Great question. It's going to be negative 0.75, right? 0.75? Yeah, that feels right. So this is going to be a negative 0.75 volts. Well, because this is negative, that means this reaction won't proceed. Chromium likes its electrons too much. It's not going to give them away to the aluminum. So this is no deal. So we just write here, no reaction. And we're done. That's it.